This is session B1, Planck's constant and quantum mechanics. So far we've been taking a sort of a historic timeline approach, saying, okay, so as physicists discover something that can't be explained with classical mechanics, we started in the 1870s and we got up to 1901, black body radiation, Max Planck. I do want to continue with the historical timeline. The next thing we should do is Einstein in 1905, but not today. What I want to do today is try something that I've not seen in books or classes. I previously said that Planck's constant appears in the equations of quantum mechanics and in all quantum mechanical results. I want to explore that a little today. In fact, I want to work from Planck's constant to develop the Schrodinger equation with you guys. Some of it will be perfectly legit, some will be hand-waving, but that's okay. At a later date, we'll do it with more care, not today. But I've never seen it done this way, and I think it will give us some insights. So I'm going to do some recap from last session. We did black body radiation. We finished it. The data was inconsistent with classical mechanics. It needed an explanation of the intensity of light from the black body. Max Planck was able to explain that. He was able to produce an equation that matched experiment very accurately, and he was able to give a physical explanation of what went wrong in classical physics for the black body radiation. He was very careful not to say anything broad about physics or light or electromagnetic radiation. He said, look, the experiment is black body radiation. I can explain it. Here's the explanation. I'm not saying more than that. Planck was an older physicist, so he was used to being cautious. In 1905, Einstein's going to come along and say, yeah, actually, that applies to all of light and all of electromagnetic radiation, not just black body radiation. Einstein is a 25-year-old brash young physicist. Einstein was right. We will see that in our next lecture. So Planck explained that electromagnetic radiation cavity modes, they're quantized. The wavelengths are quantized. The cavity has a length, and the waves, you can only have waves where an integral number of half wavelengths equals the length of the cavity. So the cavity length is L. For some particular wavelength of light, we have a wavelength lambda sub m. Divide it by 2 and we get a half wavelength. Well, we can have a particular number of, so we can have integer numbers of half wavelengths in the cavity length, and those are the only wavelengths we can have. Now, if the cavity is 10 centimeters or so, something on our scale of size, we're really going to see the quantization at microwave wavelengths, because microwave wavelengths are centimeters. But when we look at light, whose wavelengths are very small, smaller than a micron, there are going to be so many modes, because as the wavelength gets small, the number of modes gets large, and so if we look at the light spectrum is going to appear pretty continuous, but it's actually quantized. It's just very finely quantized, because the wavelength of light is so much smaller than the cavity. Now, with the wavelengths being quantized, the electromagnetic frequencies are quantized. Frequency is the speed of light over the wavelength. And what Planck said, the energy of a particular of electromagnetic radiation at a particular frequency, so the energy at some frequency, F sub m, is the energy in the cavity mode is not a continuous quantity. It's a discrete quantized quantity. It is some number n, 0, 1, 2, times a constant, little h, times the frequency of a particular frequency that we're interested in. Those are the only amounts of energy possible in the cavity modes. He used little h as his constant in his 1901 paper, and 120 years later we still reserve little h for it. Now we call it Planck's constant. He didn't call it Planck's constant. I should probably say Planck's constant, but I always call it Planck's constant anyway. So this is the formula for the energy in the energies in the cavity modes. If we look at the change in energy, well, we can go from n equals 0 to n equals 1, so the change in energy is hf. So that is the quantum of energy by which the cavity mode changes. We now call that photons, but it wasn't, Planck didn't call it photons, and I don't think Einstein called it photons. I think someone else called it photons after Einstein. So Planck said, I can explain this energy spectrum if the transfer of energy between the walls of the cavity and the electromagnetic radiation in the cavity takes place in discrete energy quanta or packets, and the energy of the packet is h times f, where f is the frequency. Since frequency is speed of light over wavelength lambda, we also have the formula hc over lambda. Frequency is the units is 1 over second or hertz. So frequency is the cycles per second. We also get a formula h over t, where t is the period, the time of a cycle. So these are all formulas we can use for discrete energy quanta of light. I said before that Planck's constant h is integral to the equations of quantum mechanics, Schrödinger's equation, and all quantum mechanical results, and I think we can discover a little bit of that today. A little bit of hand waving, but I'm not bullshitting you. It's true. I can show you pieces of it today, but even if I can't show you the entirety of it, what I'm telling you is true. So today we want to explore Planck's constant further. This is a possible time to take a break. Before I want to do one extra thing before we get that. Planck's constant is h. E equals h times f. F is frequency in hertz or cycles per second. There are places in physics and in the Schrödinger equation where we don't really want to use frequency in cycles per second. We want to use angular frequency in radians per second. I don't want to explain why that is, just take it to be true. So if we take hf and we multiply the numerator by 2 pi and we do a denominator of 2 pi, the angular frequency omega in radians per second is 2 pi times frequency. So the numerator would be h times omega, But we don't want to keep around this 2 pi in the denominator all the time, so we define a new constant, this h bar. So energy is h times f or h bar times omega, same thing. Sometimes we want to use one, sometimes the other. H bar is h over 2 pi. It's called, colloquially it's called h bar. Technically it's called the reduced Planck's constant, but quantum mechanics just calls it h bar. This is your first bit of quantum mechanics street cred. You don't have to remember the formula for h bar, but remember that there is a thing h bar. So what I said last time is that quantum mechanics equations and results use Planck's constant. That's true, but in some cases it uses Planck's constant h, and in other cases it uses reduced Planck's constant h bar. They're interchangeable. You can see they're interchangeable. It's just that we don't want to carry around this extra 2 pi when we don't have to. So we use the right one when we want to. This is a possible time to take a break. Planck's constant is a universal physical constant, sometimes called the constant of nature. There are mathematical constants, pi, e. These are numbers. They have values, but they have no units. Pi is pi for everyone. Pi would be pi for any alien civilization. They might write their numbers different, but once we understood how they write numbers, we would be able to communicate pi. But physical constants are different. They almost always have units and values. And when I say almost always, you could scratch your head and say, well, is there a physical constant that doesn't have any units? And there is, but I'm not going to tell you about it today. So almost always have units. Let's take the example, the speed of light, which we call c. In generic units, the units of speed of light are speed, which is distance over time. Before we can talk about a value for the speed of light, we need to pick a unit of distance and pick a unit of time. If we pick miles and seconds, then the speed of light is more than 186,000 miles per second. But if we pick meters as the unit of length, then the speed of light is almost 300 million meters per second. So the speed of light has a generic units, length over time, and then we pick specific units, and then it will have a single value within a definite set of real units. Okay? Now, the units of h and h bar are the same, because one is just divided by 2 pi, and 2 pi doesn't have any units. The units of h and h bar are energy times time. You probably have not encountered anything in physics which is an energy times time. But Planck had, and in fact all physicists in 1901 had studied advanced classical mechanics, and in advanced classical mechanics, specifically Hamiltonian mechanics, there is a quantity called action, which has units of energy times time. This is not Newton's third law, action and reaction. That's just a force. This is different than that. Now, since Planck knew advanced classical mechanics and knew that energy times time is an action, Planck called Planck's constant the quantum of action. It's in his paper. Physicists understood what he was talking about. Some physics books, introductory quantum mechanics books, will call it the quantum of action. This is not helpful, because nowadays physics students learn quantum mechanics first and advanced classical mechanics is a senior elective or an elective graduate course. Because you don't need it as much. We don't solve as many problems in advanced classical mechanics as they did in 1900. It's used for several problems. If you want to know how much Mars alters Earth's orbit, you'll use advanced classical mechanics. Well, you and I don't do that. We'll look it up in a book. So there are things that advanced classical mechanics is good for, but most branches of physics, you can be a PhD physicist, expert in your field, and not have to care about advanced classical mechanics, so you never took it. It was an elective. Okay? So, we are not going to call it quantum of action. If you run across a book that calls it the quantum of action, you're going to turn up your nose and say, "You bastard, you're calling it quantum of action, but you're not explaining what that means. I hate you, you suck." Okay. This is a possible time to take a break. So we're going to, instead of dwelling on what is action, we're going to try and figure out, well, what could an energy times a time be? And we're going to do that by jumping between 1901, Planck's constant, and the development of quantum mechanics in 1924 to 1927. I'm going to tell you things that are true, but I'm not going to prove them, and I'm not going to develop them the way a book will. Now, why am I doing that? Because when a book develops that, they expect you to have a certain minimum understanding of physics and electromagnetics and mathematics and calculus. And I want to see what we can learn with a little less math and a little less physics. It'll still be true, and in fact, I think it should give you some insights that the snot-nosed quantum mechanics kid may not have, even though he got an A in his course. Okay? So, now and for the next hour, we will be looking at the units of Planck's constant and getting value out of that. We're not going to look at the value of Planck's constant. The value is important. At the end of this lecture, we will look at the value, but it turns out we can get a lot of insight without caring about the value. The units tell us something. So, h bar, what are its units? Energy times time. Well, energy is an important thing. We understand energies. We understand kinetic energy and potential energy in classical physics. We understand energy in thermodynamics. We can imagine that an atom has energy. We can imagine that an electron has energy. So, energy is useful to us. Energy times time, we don't know what the heck that is. If only we divided by time, we could get rid of that time and we would end up with energy, right? So the question is how to do that. Well, we don't really have any nice way of dividing by time, but if somehow we could take h bar and multiply it times a derivative with respect to time, where a derivative is, a rate of change with respect to time. Something might change rapidly in time or slowly in time. So this derivative is a rate of change with respect to time of something, some function, which we haven't said yet. We're trying to build this up. If only we could take h bar and multiply it times a derivative with respect to time, well, that would get rid of the time part and we would only end up with an energy. And if that's on the left-hand side, and if we took a system, an atom, an electron, whatever, a system we were interested in, and we had some kind of a model of what its energy is, then we could have some kind of an equation. And maybe we could solve that equation and we could learn about an electron in an atom. That's where we're going. But right now, this is hand waving. Take h bar times the derivative with respect to time, and maybe that's some kind of an energy operator, but what the heck does this mean? Well, a derivative of what? What are we taking the derivative of? An operator operating on what? We don't know. So we'll say, well, maybe we have a state, the state of the electron in the atom. And the time derivative will operate on the state, and the energy operator will operate on the state. And if we knew what we were doing, we would have some kind of an equation. If we had an initial value of the state at some time, well, then this kind of looks like a way to find the state at all future times. So we know the state at time t equals 0, and this equation tells us the derivative with respect to time at time equals 0. So we could integrate this, or numerically we could integrate it. We could find, if we knew the state at some time, this equation would give us the state at later times. In other words, this is an equation for how the state evolves in time if somehow we know a state, which at the moment we don't. This is a possible time to take a break. Turns out this is Schrödinger's equation, which sometimes we will simplify and just call SE, Schrödinger equation, which he developed in 1925, but he developed it in a way that we're not going to do today. This is Schrödinger's equation. Technically, we should call it the time-dependent Schrödinger equation, TDSE. The part in green. This is a Greek letter, capital Psi, PSI. It is the state of the electron in the atom. It is a function of position, x, y, z, and a function of time. It appears on the left and it appears on the right. The energy operator, we're going to call that uppercase H. We give that a name, the Hamiltonian operator, but it has units of energy. So it's an energy operator, but we're going to call it the Hamiltonian operator. It is a function potentially of position, x, y, z. It is potentially a function of time, but it does not have a time derivative in it. The only time derivative is the one on the left-hand side. So the right-hand side looks like up here, energy operator operating on state, right? Hamiltonian energy operator operating on state. We haven't said what operating on means or anything yet, and we're not actually going to do that today. So there's a little bit of hand waving there. The left-hand side, here we said state, and now we have state, psi. Here we said partial derivative with respect to time, and we have partial derivative with respect to time. Here we said h bar, there's an h bar. There's only one extra thing, this I. I is the mathematical imaginary number, square root of -1. Can't explain today why it's there, but it is there. It has to be there. It has no units, so it did not violate our logic. And we can't explain why it's there, but it is there. Now, a couple things. Psi, we can call it the state function, the state vector, or the wave function. For your current level of knowledge, you can assume that all four of these are equivalent. There are distinctions, and sometimes we use one and don't use another, but we're not going to do that distinction today. At a later date, maybe we'll get that far. So if the snot-nosed kid tells you, state or state function, and you call it wave function, that's fine. Okay? So for a particular problem, we develop the correct Hamiltonian for a particular problem. The Hamiltonian involves kinetic energy and potential energy is different for different problems. So there's not one Hamiltonian. For any problem that we're working on, we have to develop the correct Hamiltonian. It's not obvious here, but, actually, do I want to? I want to say something, but I'm going to have to. Yeah, okay. I'm going to say this slightly out of order. So I said this was a time evolution. The Schrodinger equation was the time evolution, would give us the time evolution of states if only we had a state to begin with. Well, that would be a state particular to a particular Hamiltonian for a particular problem. Now, it's not obvious, but it's the Hamiltonian for a particular problem that will tell us that some energies are allowed and other energies are not. And for allowed energies, we will be able to figure out which states are allowed and which states are not. You can't see it yet, but it comes from the Hamiltonian. It does not come from the left-hand side, really. So allowed energies have names. We call them energy eigenvalues. Eigen is a German prefix meaning own, O-W-N, or self. So self values that are self to this Hamiltonian, we call them eigenvalues. Been calling that for 100 years, going to call it eigenvalues for the next 100 years. So that's your second bit of street cred, is eigenvalues. Another bit of street cred is knowing that it comes from the Hamiltonian. Now, states, valid states, for valid energy eigenvalues, we use special names. Eigenstates, eigenvectors, eigenfunctions. So we'll use eigenstate instead of state, eigenvector instead of state vector, eigenfunction instead of wave function. And again, there is slight distinction between the three, but we're not going to talk about that today. So this is a time evolution. So for a particular problem, we determine the Hamiltonian. That's easy enough, generally. More difficult is finding the allowed energies. That can be difficult. It can be difficult mathematically, or we may have to use a computer to do it. Finding the eigenstates associated with the eigenenergies also can be simple, can be difficult. And then eventually, so that was all for a fixed unit, a fixed time, t equals 0, and then we evolved that to see all future times. That's quantum mechanics in a nutshell. A book 80% of the book will be doing this for different problems. It also has to explain, well, what are these things? What are these energy eigenvalues? What are eigenstates? Do we really know where the electron is? Stuff like that. That's like 20% of the book. 80% is solving problems. We're not going to solve very many problems. We're going to try and get the lay of the land, not solve very many problems. Let's go back and review the units just to be sure. I has no units. H bar is energy times time. When we do the partial derivative with respect to time, that gets rid of time. So now we have a total of energy in here, right? Psi actually has units, but it's the same on both sides. So we're not going to care today. But it actually does have units. And the Hamiltonian H, it has units of energy. So units-wise, we're good. Okay? This is a possible time to take a break. Now, I want to say something. I want to discuss the importance of H bar here for energy transitions and emission and absorption of photons. And you're not really going to get this in a book, or you know what? It's going to assume you understand it. And I tell you, I bet 80% of students don't. So I want to cover this. I said that kind of the right-hand side lets you find all the energy eigenvalues. And let's say we're talking about a single electron in a hydrogen atom. We found its energy eigenvalues. In particular, we were interested in two of them. We found that one of them has the lowest energy that the electron can have in hydrogen. We call that the ground state. And chemists will say that that's the 1s orbital. Now, so one energy level is going to be the 1s ground state orbital. We're also, the energy level right above it is 2s and 2p. And we're going to be interested in the 2p excited orbital. And we're going to say, well, what if the electron is in the 2p orbital? It could decay into the 1s orbital, right? We know that happens. The electron emits a photon, and it simultaneously drops into the 1s orbital, and everybody's happy. How does that happen, really? Here's the way it happens. We start out with the Hamiltonian for the one electron in a hydrogen atom, and the electron is in the 2p orbital state. And this atom is all alone in its own universe. There's nothing else in its universe. There's no electromagnetic radiation, no other atoms, no other electrons, no nothing. And so we have a good Hamiltonian for the universe of one proton and one electron and nothing else in the universe. And in that universe, that electron could stay in the 2p orbital forever if there was no vacuum. But there is vacuum. The vacuum kind of talks to the atom and says, you know, we have these virtual photons here in the vacuum at just the right energy to drop you down in that ground state. Would you like one of those, virtual photons to become a real photon, and would you like to drop in the state? The atom might be the only atom in the universe, but it is surrounded by vacuum, and you can't get away from the darn vacuum, and the vacuum is not nothing. The vacuum is a very definite thing in not undergrad quantum mechanics, not graduate relativistic quantum mechanics, but in graduate quantum field theory. The vacuum is a very definite thing with photons coming and going and stealing energy and giving it back. And so with the vacuum kind of tells this Hamiltonian, I have some electromagnetic radiation of the right frequency such that HF would be exactly the right energy for you to drop down into your ground state. Would you like to do that? Vacuum talks to the atom. Well, the left-hand side here says, we have two energy levels, the 2p excited state and the 1s state. They each have their own state. There's an eigenstate for 2p, there's an eigenstate for 1s. It's more complicated than I'm showing here, but the thing is, I said this was a time evolution equation. And I said it was the left-hand side that does the time evolution. So the right side can tell us the energy difference between the 2p orbital and the 1s orbital. And this time derivative could give us a frequency of oscillating between two states. But we can't emit a photon unless that is exactly the same frequency as E equals HF, the frequency of the photon, and the energy is the energy difference between 2p and 1s. So the glue here that marries the energy difference on the right-hand side with a frequency of oscillation of the state and making that be the exact same frequency as the photon. So the photon can come out of the vacuum and become a real photon. It is this h bar. It's not enough that it's some constant with the units of energy times time. It has to be h bar. H bar is the only glue between oscillations of electron states and the frequency of a photon to match that energy. This must be h bar, and it is h bar. We got here by waving our hands, but we waved our hands exactly correct. So we just said that h bar on the left-hand side of the Schrodinger equation, it glues together differences between energy levels on the right-hand side and the right frequency of oscillation needed to emit or absorb photons. And that's great, but in the previous lecture I said that Planck's constant is present in all quantum mechanical results. It's present in energy levels, it's present in size of atoms. Well, h bar on the left-hand side doesn't do that. So it must be that there's also an h bar inside the Hamiltonian operator. That would be able to affect energy levels and aspects of the state. And so we want to see that next. This is a possible time to take a break. The Hamiltonian operator, it's an energy operator. It's the sum of a kinetic energy operator, kinetic energy being motion, and a potential energy operator that's a function of position and time. Potential energy would be like interactions between particles, electrical attraction, electrical repulsion, and many other things. We want to look at the kinetic energy operator. The kinetic energy operator, we want to start with finding a momentum operator. How can we get a momentum operator? Think about that and let's see how we get a momentum operator. We can express energy in terms of mass and velocity. Kinetic energy is 1/2 mass times velocity squared. Here we're only dealing with units, so we don't care about the 1/2. So the units of energy can be expressed as mass times velocity times velocity. The units of Planck's constant, h and h bar, are energy times time, so we have mass times velocity times time. We can group that any way we want. Let's group it as mass times velocity times time. Can you express these quantities in parentheses differently? That would help give us more insight maybe. Well, mass times velocity, that is momentum, which we normally use p to express. And velocity times time is distance or position, and we'll use x for that. So the units of Planck's constant, yes, they're energy times time. We already looked at that. But equivalently, they're momentum times distance, or momentum times position. And we can make use of that. In fact, there's going to be 4 ways that momentum times position or distance is significant to quantum mechanics in terms of units. See if you know any of these. You might not have taken a quantum mechanics course, but you might have overheard something about quantum mechanics that would be relevant here. Or you might know something about classical mechanics, momentum times distance, which would be relevant here. So think about that, and then we'll move on. So there's 4 ways, and the first one that we're going to look at is we're going to try to develop a momentum operator consistent with the Schrodinger equation. H bar we see has units of momentum times distance. So if we could divide that by distance, we would end up with momentum. So that's a start toward getting a momentum operator. Instead of dividing by distance, let's multiply by a derivative with respect to position. That would have a unit of distance in the denominator. So h bar times that would have units of momentum. So this maybe could be some kind of momentum operator, which we'll show as P with a caret or a hat, P hat, the momentum operator. And in fact, along with the Schrodinger equation, there is a quantum mechanical momentum operator. In one dimension, one Cartesian dimension, that momentum operator is minus I, where I is the imaginary number square root of minus 1, which has no units, times h bar, which is momentum times position, times a derivative with respect to x. We're only dealing with one dimension here. So this collectively has units of momentum, and it is an operator. It's a derivative. So this is a momentum operator. In this lecture, we're not prepared to say why there's a minus I here, but there is, and we'll talk about that in a future lecture. Remember, at this point, we're just kind of hand-waving correctly, but hand-waving. So that is a quantum mechanical momentum operator in the x direction. What is the kinetic energy operator? Well, kinetic energy is 1/2 mass times velocity squared, or momentum squared divided by 2 times mass. We only did the momentum operator in 1 dimension, but if we were to do it in 3 Cartesian, in 3 dimensions in Cartesian space, the kinetic energy operator would be p squared over 2m. Well, when we do p squared, this minus I squared is going to give us a minus sign. H bar squared is here, over 2 times mass, and then the derivative, the second derivative is going to be like this. Second derivative with respect to x squared plus second derivative with respect to y squared plus second derivative with respect to z squared. If we were using cylindrical coordinates or spherical coordinates, it would be different and more complicated, but well understood in classical physics. So, the Hamiltonian operator is the sum of a kinetic energy operator, which is all this stuff that we just did, plus a potential energy operator, which will be a function of space and time. This will be different for every separate problem. We're not going to put in specific problem functions for the potential energy today. So now that we have a Hamiltonian operator, let's go back. So this was, Hamiltonian operator was included in Schrödinger's 1925 paper about Schrödinger's wave mechanics. Now, H bar does appear in the Hamiltonian. As we said, well, it better if it's going to be able to affect energy levels, sizes of atoms, and so forth. So H bar appears on the left-hand side dealing with time, and on the right-hand side dealing with momentum. It's therefore going to appear in every quantum mechanical result: energies, atomic sizes, bond lengths, etc. But the H bar on the right-hand side of Schrödinger's equation is not central to the frequencies of photons that are being emitted and absorbed. It is central to energy levels, but the H bar on the left-hand side of Schrödinger's equation, that deals with photon frequencies. So that's the first case where we can use the units of H bar as momentum times position to get some insight into quantum mechanics. This is a possible time to take a break. Here's the second example that we're going to use. Heisenberg's Uncertainty Principle, which he published in 1927. So published after Schrödinger equation, but Heisenberg had been working on his own variety of quantum mechanics since before Schrödinger. So this paper is not derivative of Schrödinger equation. It's Heisenberg's unique work. You may have heard of Heisenberg Uncertainty Principle, even though you haven't had a quantum mechanics course. We'll deal with it at that level. We can measure a particle's position. Classically, we can measure it. We can measure a particle's momentum. Classically, we can measure that. When we make measurements, they'll have some precision that we want to aim for some precision in our measurements, and there's going to be some uncertainty in the results. Some of the uncertainty in the results is due to just the reality of making measurements. But we're going to find, and classically, that would be the only limit to precision classically. We're going to find out that with quantum mechanics and systems on the size scale of atoms, that measurement is not the only limitation. A measurement setup is not the only limitation to the precision that we can get in our measurements. Let's consider some specific measurements on a particle. We'll deal with one dimension. We want to measure position. There's going to be some uncertainty in the position measurement. We'll call that delta x. We want to measure momentum in that direction, and there'll be some uncertainty in that momentum measurement. We'll call that delta p sub x. In Heisenberg's Uncertainty Principle says that for any and every measurement you can possibly take of any and every possible system in any state at any time, no matter what you do, the uncertainty in measuring x position times the uncertainty in measuring the position in the x direction measured at the same time, the product of those uncertainties is going to be greater than or equal to h bar over 2, no matter what you do. There's nothing you can do to do better than that. It doesn't say you can't measure position very accurately. But it says is if you're doing a measurement that you're trying to make the position measurement very accurate, a measurement of momentum in that direction would be less accurate. And vice versa. Let's look at this for units. We said h bar, we can look at the units of h bar as position times momentum, and that is what the units on the left-hand side are. Uncertainty in position times uncertainty in momentum. So unit-wise, it's fine. We see our friend h bar in there. So you cannot simultaneously measure position and momentum in the same direction to arbitrary position in quantum mechanics. In classical mechanics, we assume you could. It's an assumption in classical mechanics that, oh yeah, you can do this. Just make your measurements better and better. And it's built into classical mechanics that, okay, well, once you've figured out your position perfectly and your momentum perfectly and you know your forces, then you can calculate your position and momentum perfectly for all future times. So that's all you need to know is your position and momentum at some time, and classically, and your forces. And in principle, you can then solve for your position and momentum to arbitrary accuracy for all future time. Quantum mechanics says, no, you can't. You just can't. There's limits to it. You can't beat the limit. That's all she wrote. Now, we've never tried in classical mechanics of macroscopic objects to get the precisions of position and momentum simultaneously so precise that we could have discovered this inequality. This is small compared to macroscopic measurements, macroscopic systems and their measurements. Now, we should also think about this in another way. If we're trying to measure position and then very shortly thereafter measure momentum, to sneak up on it, not simultaneously, but we'll get a very accurate measurement of position, and then immediately after we'll get a very accurate measurement of momentum, and so therefore we'll pretty much know where it was and how fast it was going. Quantum mechanics says, nah, you can't do that. When you make the measurement of of position, you can get back a very accurate measurement, but the measurement process itself impacted and randomized the momentum instantaneously. So if a short time later, 1 nanosecond later, you then measure momentum, you will be able to measure momentum and you will be able to measure it accurately, but it will not be the momentum that it was 1 nanosecond earlier, because the measurement of position altered the system state. Same thing if you do it in the other direction. This is different than classical mechanics. Now, it turns out you can simultaneously measure position and momentum to arbitrary precision if they're in different directions. We can simultaneously measure x position and y momentum, and we can measure them both perfectly precisely to the extent that we can do the measurement with a real world measurement setup. There's no quantum mechanical limitation to the product of those uncertainties because they're in different directions. They're in orthogonal directions. You can measure the x position and the z momentum simultaneously, but you cannot measure the x position and the x momentum simultaneously to arbitrary position. So that's the second interesting use of h-bar. Now, you could say, well, that's Heisenberg's uncertainty principle. I don't see that in the Schrodinger equation. And you're right, you don't see it, but it's actually in there in subtle ways that it takes some effort to see. So, solutions to Schrodinger's equation, states to Schrodinger's equation, do obey Heisenberg's uncertainty principle, but it's not obvious and it takes some work to show it. This is a possible time to take a break. What's our third use of h-bar? It's called the de Broglie relation, and it was published in 1924, so before 1925 when Schrodinger published Schrodinger equation. I don't speak French, but I'm told that his name should be pronounced de Broglie, but the physics professor that I had when I was learning, first I came across this in a book and didn't know how to pronounce it, and then the physics professors that I've had more often pronounce it de Broglie instead of de Broglie, so I guess I'm in that bad habit. If you're a French speaker, feel free to pronounce it correctly. In some respects, a particle with momentum p, magnitude of momentum p, we'll talk about one direction so we don't have to worry about the direction of p. A particle with momentum magnitude p can be considered to have a wavelength. Even though we called it a particle, it kind of has a wavelength. And the wavelength lambda has value h over p. Now this h is not h bar, it's h. Let's look at this units. H has units, momentum times position or distance. So if we divide out the momentum, we end up with a position or distance, and wavelength has units of distance. So unit-wise, it works fine. If the wavelength from this de Broglie formula is much less than the particle's size, the particle's motion might be classical, probably is classical, and not require quantum mechanics. But if the wavelength from this formula is comparable to the particle size or larger than the particle size, we almost certainly need to use quantum mechanics. So this can be a way for us to gauge, do we have to use quantum mechanics or can we use classical mechanics? It's a little subtle. We're gonna talk about this more in a future lecture. If I talk about the subtleties now, it may confuse you in a way that I don't want to confuse you. So in a later lecture, I want to talk about how did de Broglie come to this relationship. It was his PhD thesis, and he got a Nobel Prize for it, and he basically was he was reinterpreting some work that Einstein did in 1905. But in the 19 years between 1905 and 1924, nobody else had done it. So, an interesting situation. We'll talk about it more in another lecture. But it is a use of h. In this case, h, not h bar. This is a possible time to take a break. The fourth instance is angular momentum. This will be important in quantum mechanics in 1913 when Bohr develops his Bohr model for hydrogen, and in 1925 after Schrodinger develops a Schrodinger equation. This might be a surprise. Why are we talking about angular momentum? I mean, we talked about black body radiation. We never ever talked about angular momentum there. Nothing was rotating. How come we could talk about angular momentum now? Let's see. You might or might not be familiar from physics with orbital angular momentum. From high school physics, you may have had orbital angular momentum just dealing in one direction, not as vectors. If you took college physics, you may have learned that the orbital angular momentum vector is equal to the position vector cross product with the momentum vector. For example, for a particle or an object orbiting a point. We don't need to care about the details of that vector formula. Let's look at it in terms of units. Well, the position vector has units of position or distance. Momentum has units of momentum. When we multiply them together, we get distance times momentum. That's the same units as Planck's constant. So angular momentum has the same units as Planck's constant. That's kind of interesting. We don't know it yet. We'll learn it when we do the Bohr model of hydrogen. But in the Bohr model for a hydrogen atom, Bohr proposes that the electron is in certain circular orbits around the proton, around the nucleus. We now know that's not true, but it was useful, and it predicted some otherwise impossible to predict correct results. In the Bohr model, you could only have certain orbits, certain distances between circular orbits, and you could only have certain distances between the electron and the proton. And as a result of the electrostatic attraction between them, when you crank it through, the orbital distance determines the momentum. In this case, it's a tangential momentum. It's a momentum around the orbit. And it turns out that if you calculate angular momentum in the Bohr model, it can only have certain values. And they're quantized in units of h bar. So you can have in the Bohr model, you can have an orbit where the integer L is 0, actually there's an error here. So in the true correct hydrogen atom, you can have L equals 0 and have 0 orbital angular momentum. Or L can be 1 or 2. In the Bohr model, it starts with 1. So you can have 1, 2, 3, and so on for circular orbits. But in the real actual hydrogen atom that we would get from Schrödinger equation, the value L equals 0 is also allowed. So in that case, there would be 0 orbital angular momentum. So orbital angular momentum is quantized in the real hydrogen atom. It is an integer times h bar. That has the right units for angular momentum. However, don't ever believe or think that the electron is really orbiting the nucleus or that it has any trajectory at all. When you take general science or high school physics, or high school chemistry, they will show you, the electron orbiting the nucleus. That's just not how it really works in quantum mechanics. It's a nice visual image. It's just not true. And therefore, it's confusing to you when you want to really understand, well, what is it really doing and what is quantum mechanics have to say? So there are no circular orbits, but there is orbital angular momentum. Well, what the heck? Can that even be true? Simply, naively, we think that angular momentum is, well, that's what circular orbits look like. But you can have angular momentum without having circular orbits. So let me show you the following. Here is the nucleus of the atom, at this crosshair. What I've done here is I've taken various starting positions of an electron that is bound to this nucleus, and I've drawn a whole bunch of momentum vectors starting from the different positions. Every one of these momentum vectors, starting from its starting position, they all have the same orbital angular momentum. It's hard to visualize because we're used to thinking of circular orbits, but an electron that starts here and has this momentum has the same orbital angular momentum as an electron that starts here and has this momentum or this momentum. So if you believe me with this chart, you should not think of an orbital angular momentum as meaning a circular orbit. In fact, in quantum mechanics, not only are there not orbits, there are not trajectories. We cannot say that an electron started here and had this momentum, because we already learned that in Heisenberg's Uncertainty Principle, if we know this x position very accurately, then we cannot know the x momentum very accurately, because the product of the uncertainties has a lower bound, h bar over 2. So even just drawing these arrows is wrong, because it should be a smeared out arrow. Every one of these should be smeared out. And so really this whole picture should be smeared out. Now, I don't want to scare you into thinking, oh, well, we can't know anything. There are things we can know absolutely in quantum mechanics. We can know energies precisely. We can know orbital angular momentum precisely. But we cannot know position and momentum in the same direction precisely. So there are not circular orbits, there are not trajectories. Why is saying that orbital angular momentum is quantized which means it's constant and conserved. How is that consistent with Heisenberg's uncertainty principle, which says if we knew a position very accurately, we could not know the momentum very accurately? Well, Heisenberg's uncertainty principle deals with measuring position and momentum in the same direction. We can measure position in one direction and momentum in an orthogonal direction. We can simultaneously measure them simultaneously accurately. And that characteristic, think of it as a loophole if you want, that is what is consistent with our having orbital angular momentum and being able to measure it accurately and it being quantized. Okay, we've exhausted playing with units. I hope you've come to feel that this was worthwhile and you have some insight. It's not the approach a book will take. A book will quickly get you to the de Broglie relationship and then to Schrödinger's equation, and then you will solve some problems, and you will then look at one of those problems and you will then develop Heisenberg's uncertainty principle. You won't deal with angular momentum until you deal with the hydrogen atom. That's the normal way of teaching you quantum mechanics. That's fine. It requires a certain amount of ability in math and a certain amount of ability in physics, which we are going to do later, but I wanted to see how much we could do without that first. So we've exhausted the units of Planck's constant. This is a possible time to take a break. Now let's look at the value of Planck's constant. The value matters. The value is the difference between when we can use classical mechanics and when we must use quantum mechanics. A lot of the principles of quantum mechanics don't depend on the value of Planck's constant, but solving any actual problem and getting an answer, if we want a numerical answer, we have to use Planck's constant. So we do want to look at its value. Planck's constant and the reduced Planck's constant h bar, they have units of energy times time. To look at value, we need to pick an energy unit and a time unit. We're always going to use seconds for time. In classical mechanics, we normally would use joule for energy. Joule is a Newton meter. This is SI units or MKS, meter kilogram second units. Joule is a unit that is macroscopic. It's on our scale. It's too big for atomic energy levels and for wavelengths of light that we care about, visible light. So electron volt is a nice bite-sized energy unit. It is what we use in quantum mechanics. You're probably not familiar with it. You might be familiar with a volt, though. Car batteries for gasoline and diesel cars, the car battery is usually 12 volts. You might know what that means, maybe you don't, but at least it's something you can remember, 12 volts. What is an electron volt? If an electron comes out of that battery and goes down a circuit and goes to the other terminal of the battery, the total amount of energy that will be given to that electron is 12 electron volts because it's one electron and a 12-volt battery. So even though you're not really familiar with electron volts or volts, you can maybe imagine your car and think, okay, well, I don't know what it is, but an electron would get 12 of them in going between these two terminals. We'll have a better appreciation when we actually do some calculations. But for now, we'll leave it at that. So here are the values of h and h bar in joules seconds or electron volt seconds. The electron volt second number looks small, and so h bar is just h over 2 pi. If you were to do the calculation, you would see. But I'm giving you both because sometimes you use h, sometimes you use h bar. Why should you have to do the divide by 2 pi if it can be in a table? So these values, we jump to the conclusion that these seem small because the power of 10, I mean, it seems small. Isn't it small? 10 to the minus 15, 10 to the minus 16? That must be small. Well, we don't know if that's big or small until we actually do some calculations. So we will see. Now, it's also handy to have in the table Planck's constant h times the speed of light. The speed of light is meters per second. So when we multiply this, instead of seconds, we get meters. So joule meters or electron volt meters. And there, even though we don't really know what this electron volt meters is, the exponent is not that high, 10 to the minus 6. So we'll see more. The reason why we want this hc, you might remember that the energy of a photon is h times f, but it also can be expressed as hc over lambda. Let's do some calculations. Visible light wavelengths range from 400 nanometers for violet to 700 nanometers for red. Now, nano is 10 to the minus 9, so 400 times 10 to the minus 9 meters for violet. Violet is smaller wavelength, higher energy than red. Let's calculate photon energy for a particular wavelength lambda. It's hc over lambda, and we'll just pull out this value for hc. 1.24 by 10 to the minus 6 electron volts, which we write as EV, times meters divided by lambda, where lambda is the wavelength in meters. Let's use the example of violet, 400 nanometers. This over 400 nanometers, we get 3.1 electron volts. Well, okay, I mean, we don't really have a strong feeling for electron volts yet, but I said that an electron picks up 12 electron volts in going through the battery. And here we see, we know what violet, we know the color violet. And here I'm saying that the amount of energy in one photon of violet is 3.1 electron volts. Okay, well, with some practice, you can get a feel for electron volts just by thinking about the amount of energy in violet and red photons. If we do red, we would get 1.77 eV. So the visible spectrum is like between 2 to 3 electron volts. Now, it turns out that the energy levels for electrons in atoms are on the order of this scale also. They could be less than an electron volt, they could be 1 to 2 electron volts, they could be 13 electron volts, but they're in this range. So we don't have to keep around powers of 10 for these photons or those energy levels of electrons in atoms, which is why electron volt is a good unit for that. Now, if we had a photon with a wavelength of 1 micrometer, 10 to the minus 6 meters, or 1,000 nanometers, it would have a longer wavelength than red. 1,000 is longer than 700. So it would be infrared. We can't see it. It's less energy, longer wavelength than red. And a 1 micrometer or 1 micron infrared photon is 1.24 eV. That's something you could memorize if you wanted to. So infrared photons have energies less than 1.77 eV. Ultraviolet photons have energy more than 3.1 eV and smaller wavelength than 400 nanometers. But those aren't the only kinds of light or photons or electromagnetic radiation. Photon energies span 27 orders of magnitude. Extremely low frequency radio waves, the energy of a photon is 10 to the minus 14th electron volts. There are gamma rays hitting the Earth that have energy as high as 10 to the plus 13 electron volts. So the visible light is kind of right smack in the middle of the spectrum. And so we've picked a good unit for energy for Planck's constant. This is a possible time to take a break. Books will tell you that Planck's constant is small. Well, okay, I hate when anybody ever says that something is small or big. Well, that's all relative. Smaller than what? Bigger than what? If you just say that something is just small, you're assuming a comparison without telling the other person what you're comparing against. So you need to see different results to get a feel for is Planck's constant small. The smallness of Planck's constant separates the quantum world from the classical macroscopic world. That's true, but what do we mean? Well, one thing that we kind of mean is the de Broglie or de Broglie wavelength. If Planck's constant and some momentum makes the wavelength of an object larger than the system that it's in, then that is classical. Then that is quantum mechanical. But if we pick a macroscopic object, like a baseball that I'm throwing, and we calculate its de Broglie wavelength, it's going to be way wicked smaller than the size of the baseball. And so that baseball is going to behave classically. We don't need quantum mechanics for it. So when we say that Planck's constant is small, we're kind of saying the de Broglie wavelength for macroscopic objects, baseballs, our bodies, Planck's constant is small enough that those wavelengths are small enough that those objects are classical. But Planck's constant is not small when we talk about an electron in an atom. It's plenty big. So we have to be careful when we say Planck's constant is small without saying smaller than what. We will talk about this in a future lecture. This is a possible time to take a break. How well do we know Planck's constant? I gave you the values, but how accurately are they known? Planck's constant is known to 9 significant figure precision. So pretty darn accurate. That's more accurate than a lot of fundamental constants, constants of nature. But is that how accurately we know quantum mechanics? Actually, we know quantum mechanics more accurately than that. And we'll talk about that. We'll talk about that in a few minutes. You could say, is there just one Planck's constant? Or is there one for photons, one for electrons, one for neutrons? Physicists have done the experiment and tried to find a difference in value of Planck's constant for those three. And any difference is less than 10 to the minus 8, which is consistent with the precision that we know for Planck's constant. So as far as we know, there is just one Planck's constant, whether we're talking about photons, electrons, neutrons, atoms, molecules, as far as we know. Well, is Planck's constant measured on Earth the same as it is in the Sun, or in the Andromeda Galaxy, or in a galaxy far away, or a galaxy from a long time ago? Physicists know that Planck's constant, there is less than a 1 part per million difference between Planck's constant measured here on Earth today versus in a star in galaxy 12 billion years ago, where light has been traveling 12 billion light years to reach us. How do we know this? You might want to think about that and then come back to the video. The way we know this, several lectures ago we talked about absorption lines in light coming from the sun or other stars. And there were found to be patterns of those absorption lines, and those patterns could be perfectly matched to emission lines of elements on Earth. Hydrogen and other oxygen and neon, other elements on Earth. Well, the light from galaxies from 12 billion years ago, that also has absorption lines. And although they're shifted because the universe is expanding, which is not quantum mechanics, that's general relativity and astronomy and cosmology, they're shifted, but the shifting does not change the pattern, and we can match up the pattern. And so we can see from light from stars 12 billion years ago, and we could tell what atoms were in the outer gaseous skin of the star. And we can also check the value of Planck's constant that produces those patterns from, we could check that star from 12 billion years ago against here on Earth, and it differs by less than 1 part per million. So that lets us say that Planck's constant is a universal physical constant. We know it for most of the 13 point something billion years of our observable universe. Physicists believe that Planck's constant is unchanged since our Big Bang, but they only know it, they only have evidence back 12 billion years ago. So 12 billion out of 13.6 billion. So it's a universal physical constant. It turns out that an electron behaves very slightly like a little bar magnet. It has a little bit of magnetism. It's due to an intrinsic property in every electron in the universe called spin angular momentum, and the fact that the electron has a charge. So there's a physics term called the magnetic moment of the electron, which is good enough for us. We will consider that to be the strength of its little bar magnet. We can measure that. We could take big macroscopic magnets and shoot electrons across magnets and make measurements. So we can experimentally determine the magnetic moment of the electron. It can also be calculated, but it can't be calculated from ordinary undergraduate non-relativistic quantum mechanics. It requires a complicated graduate quantum electrodynamics field theory, which is shortened to the acronym QED, quantum electrodynamics. That calculates everything that can be known about an electron. It turns out that theory can be simulated on a computer very accurately. It can be simulated up to 13 significant figure accuracy, and experimentally it can be measured to 13 significant figure accuracy, and they agree to 13 significant figures. So even though we know Planck's constant to 9 significant figures, which is pretty good, but we know the magnetic moment of an electron, theory and experiment, to 13 significant figures. That is the most successful agreement. It's the most successful theoretical prediction and experimental agreement of any scientific theory in any field, which is why we believe in quantum mechanics, and we believe some of the weird things quantum mechanics tells us about what we can and cannot observe in our world and our universe. In part, we believe it because we've never yet found a case where quantum mechanics was wrong, and because we are able to predict and experimentally test at least one thing, the magnetic moment of the electron, to better precision than any other scientific theory. So, as we learn some things about quantum mechanics that seem very weird, and we're tempted to say, well, this is just BS, the thing is, the predictions that quantum mechanics makes are testable and have always proven correct whenever they've been tested. So, we might have trouble understanding some of them, we might have trouble believing them, but we can't really ignore them because they can be tested and they do test successfully. That's the end of this lecture. Next time, we will go back to the historical timeline. We'll go back to 1905 and Einstein's miracle year.